a minute and find on your calculator, you see where your E button is, your E to a power button. So it's not the button that says E. It's not the one right above the comma, right? That EE is actually times 10 to the, that's your scientific notation button.
Oh, I see it.
E to the X is right above the LN.
Yeah.
Okay, so if I had to do, for example, let's make sure everybody can do this. If I had to do E to the, somebody first, before you do it in the calculator, about how much should this be, E squared? About how much?
4, 5.
And you're basing that on what fact? Remember, E is 2.7, it's closer to 3.
Should be 7.
So this should be kind of close to 9. So 7, something like that. Alright, let's try it. What is E squared?
7.389. 0,
Cool.
5.
Mine says E squared is E squared.
Oh my gosh. It is profound. E squared. Is E squared. I don't like that. What's 4 plus 7? 4 plus 7. That's funky. So you have 89 or
Inspired.
oh, the inspired. You got it set on some kind of funky. The view is set to be exact instead of approximate. So I'm not sure how to change it, to tell you honestly. Somewhere it says exact and approximate.
Approximate subtraction.
Yeah, approximate, yeah.
I got 5,300,000 over 7,000,000.
Maybe if you divide it, you're right. Holy crap. This is funky. Alright, anyway. So we'll work with you here in a minute. Everybody else try E to the negative 5.
I got 0.0067.
So be real careful. On your calculator, there's a negative sign and there's a minus sign. Alright, the negative sign is right above the, not right above the, right at the bottom of this calculator. That's a negative. Cool. So you have 0.0067. Blah, blah, blah. Okay, cool. Just make sure everybody knows where their E button is and how to use it. And we'll figure that one out in the back somehow. Okay. So really, how do you think the E function is going to look when you graph it? I mean, what should it be between the graphs of that we know? What is E itself between? 2 and 3. So it should be between the graphs of 2 to the x and 3 to the x, right? So if I were to graph E to the x, I can graph 2 to the x. Let me see if you guys can do this. Can somebody give me like the three basic points that's on 2 to the x?
1/2.
Alright, so that's a part of a point.
What is it? 0, 1/2. 0, negative 1. Oh.
0, 1, let's start there. So you always have 0, 1. Cool. As long as it hasn't been shifted, you always have 0, 1. You have, when you get to 1/2, when it's
negative.
negative 1. And at 1 it's 2. Those are what I call my 3 anchor points. So if I have a problem where I have to shift the base graph, I graph those points and then I move those around. Because that gives me the shape. I know it's going to go crazy up from there, and I know it's going to go really close to 0 there. I just need those 3 points to really get the shape. And then, how would I graph 3 to the x? So it's not f of x yet. 3 to the x would be the same stuff, except now it's 1/3 here, right? It's still 0, 1 there. And at 1, it's going to be 3. So E to the x would have to live right in between those. Because E itself is right in between 2 and 3. Cool. So I really, when you're doing the problems in section 4.2, you don't have to be perfect, obviously, because your base is freaking 2.712, blah, blah, blah. You're not going to be perfect. But I just want to give you an idea about where this should be. When you do e to the first power, it should be about 2.7. That would be right in between the blue and the purple, right? You guys kind of with me? Yeah. E to the first power is going to be about 2.7. E to the 0 power, what's e to the 0 power? 1. And e to the negative 1, it's almost 1/3 in a way, right? You with me? So it's going to actually be right between those points, but that's e to the x. It lives right in between 2 to the x and 3 to the x. So 4.2 has got nothing new in terms of what they ask you to do. They just throw it as this special base, this e base. And e comes from a lot of different things. E is the easiest thing to use to model, like I said earlier, radioactive decay, population growth. Because you can actually use directly in its power, you can use the rate of growth or the rate of decay. So if anybody here taking chemistry? Does this sound at all familiar? Rate of decay? So we guys like, no, we had a terrible time. All right. So my point with this is 4.2 is very much like 4.1. And what they ask you to do, they just ask you to do it with E base instead of 7 or 4 or 2 base. Let's try one of these that's a little more interesting here. Look at number 21 on page 313. This is a little word problem, sort of. Let me tell you this. It's a wordy problem. No, it's not a word. It's a problem that's got more words than the others. So it says a radioactive substance decays in such a way that the amount of mass remaining after T days is given by this function. Stay with me.
Is that T?
T, yeah. This is trying to be an M for mass. And this is in, did they tell me? Kilograms. Can somebody tell me how much of the substance I had at the very beginning, before any of it started to decay? And what would that T value be for the very beginning? 0. So if I plug a T equals 0 in, what's M of 0? 13e to the negative 0.15 times 0. And what's e to the 0? So I started with 13 kilograms of this stuff. Is that one question they ask us? Oh yeah, okay. It's your standard question. How much did you have to start with? We plug a 0 in because no time has gone by. You with me? So T is truly the time that's gone by. Okay. Then they ask you how much is left after 45 days. Do it. T is in days. Yeah, thank you. If he was in hours, that would be kind of easy. 45. So part B, this is part A. Part B says, how much mass after 45 days? Hold on. And be careful. What'd you say? 25? Be careful now. Think about it. If I add 13 to begin with, and it's decaying.
Oh, I forgot.
Yeah, cool. The thing to be really careful about in your calculator is you got to say 13 times e to the, in parentheses, you want to put this. If you don't, it's going to raise e to this power, and then whatever that is, it's going to multiply by this because it knows order operation. So you better put your power, oops, what your power is going to be, you better put it in parentheses. So it knows that you raise it to the whole thing. So this would be 13e to the negative 0.015 times 45. So you get what now? 6 point?
619.
Kilograms. I like it. Okay. So I like that problem because it's kind of like coming off of what I just said. Exponentials are used in things like radioactive decay. They're used in population growth. Do they have population growth? Yeah, sort of. Bird population. World population, blah, blah, blah. Cool. All right. So what I really want to focus attention on today, and I did kind of go a little bit quickly through 4142, because it really should, for the most part, be a review. If it isn't, you might want to come see me or a tutor and fill in some gaps. I want to focus my time on 4.3 because even if you make it to that point, very often Math 110's teachers don't make it to logarithms, which kind of sucks. Even if you did make it to that point, very often logarithms are not fully understood by students. Right? And logarithms are used a lot. Can't stress that enough. They're used a lot. You're going to see them very often in calculus if you go that far, in this class, and you are here. Okay. So I teach this in a way that makes it feel like logarithms came after exponentials, but the truth is they came before. Right, there's a guy named Napier. I don't know if you guys ever heard John Napier. I just want to throw it out there. There's an off chance. So he came up with the idea, and somebody else came up with the idea at the same time. It just took him longer to publish the results, so of course we all credit to one dude that got quicker. He wanted a way to figure out how to multiply things quickly. And have you guys ever heard of logarithmic tables?
Yeah.
You guys ever heard of slide rules? You ever seen a slide rule before? You have no idea what I'm talking about. They're sort of like 8-track tapes, or for me. They're like slide rules are from the 30s, 40s, even before that. I have a circular one that's kind of cool. But slide rules, these and log tables obviously are based on logarithms. They use a property of logarithms to make it easier to multiply large numbers, several large numbers together. And this is obviously before we had calculators. So now we have calculators, you don't see logarithmic tables anymore, because who the hell wants it? So, I just want to make sure that you understand that. I'm going to teach it coming off of exponential functions. Historically, they came before, to be completely honest, and they weren't made, the connection wasn't made until much after that. So if I have a function, let's start with a nice little function, 2 to the x. That's easy enough.
And this is 4.3.
This is 4.3. Guys, take a minute and just do a quick graph of that. Get those 3 basic points that help you graph that. Start this back up. Yep. Alright, so what 3 basic points can you use for this guy?
-1, 0.
Yeah, -1, 1/2, 0, 1, 1, 2. Okay. And it's not at all. Like that, roughly. Can you now, on top of that, graph what the inverse function would look like? Does this have an inverse function first? It's a very good question. Jeff, should we even try this shit? Does it have an inverse function?
Yeah.
Yes, because it passes Horizontal line test. Cool. So there's a reason to do this. So graph. We don't even know what the hell this function is we're graphing, but we can graph the inverse function. So f goes through and what's really interesting is the asymptote right now is the x-axis. Once you flip that bad boy, it's now going to be the y-axis. Yeah. Neat. So here's something you can always do if I ask you to do this kind of problem. List the points that you know for sure f goes through. Now what does f inverse go through? 1/2, -1. Right, so it goes through 1/2, -1, 1, 0, and 2, 1. And it's got to be symmetric here, right? You say so, Jeff. And you can see that if I kept going, -2 would be 1/4. So 1/4 would go to -2. You can see that this is going to be asymptotic here. So it's going to be like this. So you can see that symmetry there. Okay, how are we doing so far? We're doing good? Okay. So we at least have a graph. We at least have a visual of what the opposite function is for this guy. And let me do this to help us out a little bit. If I ask you, well, let's do this. I want something that's actually invertible. If I said what cubed equals 27, 3. And you know, what cubed equals 8, 2, and you know, amazing stuff like that. We don't like that in mathematics. We want to have the idea of an input and an output. So in this case, before I put the 3 in there, what's really my input? 27. I'm trying to figure out what the output is. Truly. Right? Because what do I keep changing when I went from this to this to this? What am I changing? I'm changing this number here, aren't I? Well, what if I put a 27 there? What if I put an 8 there? Isn't that my input then? I want to be able to write this in a form that makes it clear that that's my input. So here's one reason that you guys are like, what the frick? I like talking about roots and powers when I start talking about logarithms because they have a lot of similarities. They're not exactly the same, be careful. One cool similarity they have is they had to come up with a symbol. They wanted this to be more like, so if I have this, they wanted some function of 27 to come out to be 3. You with me? Yeah? So they had to come up with a symbol. And they couldn't just use f. That already means some unknown function. So they used the symbol, they had the radical, and just to make it more clear, they wanted it to be the opposite of a cube. So they put a little 3 up there so everybody knew it was undo a cube. How we doing? Okay, so this is kind of cool too. So now you have much more of a input, output. So we have the same problem here, really. I could ask you, what would I put here to have, what, Jeff? 1/2 come out. -1. You want to flip it, right? So then the input was 1/2. The output was -1. So you see how that process is really describing the blue line? The problem is I've got it written using f. I want to know how the hell to write f inverse by himself. Everything in mathematics was a choice at one time or another. You all were born too late to have any say in it. Right? I'd rather be born around now instead of the 1300s. Thank you very much. You with me? Not on that, but in general. So they just had to come up with a symbol that would do the opposite, that would have this as an input and then -1 as an output. If I write on this, it looks like that was the input. No, it wasn't. Wasn't that my input just a second ago? And you guys had to figure out what that was? I desperately want you to understand that. It could have been anything. They could have put a little box around there with a dot on the top and said, that's the inverse function. Yeah. But unfortunately, we weren't there. Instead, they used and just like the 3 had to be there so that we knew it came from a cube, the 2 has to be here so I know it came from a base 2. So then log base 2 of 1/2 is -1. Oh shit. That's right. What did I just say? Alright, so let me come at you again. You guys are all cool when I said that. What 2 to what power is, let me see if you guys can do this. 2 to what power is 1/8?
-2. -3.
-3. You gotta flip it, and I gotta make it 8. You with me? 2 cubed is 8. It's gotta be -3 to make it flip. So log base 2 of 1/8 is asking you the same freaking question. That's all. That's all it is. It could have been any symbol that you wanted. They used logarithmos because we weren't around to say, hey, we should use something else. No, we weren't around, right? And that actually has to do with ratios of, I can't remember now. Anything that has to do with, we'll see later that a logarithm is really used for ratios for a lot of times, to rewrite ratios. But all that stuff aside, when I ask you this, when I put it like this, you guys can figure out -3 pretty easily. Same damn question. 2, so what power is 1/8? -3. So the answer, now here's a key. Sounds like a real big note coming up. We don't do this very often. The answer to a logarithm is always a power. Right?
Okay.
What do I raise the base to make this happen? You with me? Shit. So, log base 3 of 27. The question you ask yourself is, what power do I need to put on this to make it become this? There you go.
Isn't that the sliding trick where you just slide the bottom one? Like,
oh, you go.
just
Oh
knock it
yeah.
up.
I think
slide.
you taught me like this
Slide.
loop thing.
So you get the 3, like, without the other 3 there,
Oh,
you
yeah,
slide
yeah.
in.
We'll go up there. Yeah, I'm with you.
Yeah, what's the, yeah, what would make that, whatever.
That's to check yourself with, right?
Yeah.
You can, that's going to be, you got to be careful because it's not going to go up here. It's going to be the base. That's going to be the power.
That's what I meant. Like, you just slide it and then what was that?
Gotcha. All right.
Yeah.
A little bit.
Great.
I'll show you. Hold on. Because you could rewrite. Now, all right. My philosophy on tricks is that as long as it's built in that you won't forget why it works. So I'm really careful about doing things that don't gloss over the idea. Because the more you do that kind of thing, the less connection you're going to have to what you're doing. The more you're going to know, this is what I do, and the less you're going to know, this is why I do it. And then you can't make connections later. I do this, though. How can I rewrite this in exponential form? This is logarithmic form. And exponential form is exactly the way we figure this out. 2 to the -3rd is 1/8. How we doing? Notice something. What's the input here? What's the input here? 1/8. What's the output there? Isn't that what inverse functions are supposed to do? The input of one is the output of the other and vice versa. Okay, maybe. Let's do several more before we lose what this is. How about this? Let me freak you out. What's log base 1/4 of 16?
4.
-4.
-4.
-2. 4.
1/4 to the
What if you do the 4 to make it 16? Square it. So make 1/4 16, -2. You with me? So what's more important there is that you right now you understand how to attack this problem. It's not going to be immediate a lot of times. In fact, I'm being very careful how I'm setting this up, Art. If I would have put a 15 there, could you have given me the exact answer? No. Ain't no way in hell. You could say around -2, but you can't give me the exact answer. We don't know how to do that yet. Is there a log base 1/4 button on your calculator?
No.
No. I don't care what calculator you got. Alright, so thankfully we're gonna learn a way around that I can actually use the calculator no matter what the hell base. We'll learn a way around that. So let's try one that's not so freaky. What about log base? I don't know. What's log base 5 of 1? I like that.
0.
I love it. So log base almost anything of 1 is 0. Why? Because 5 to the, how do we write this? 5
Equals
to the 0 is 1. There you go. How about this? Rewrite this in exponential form.
I got it.
Not this, but right. Sorry. How you doing? I have shush Tourette's. Sorry. Let me tell you a story about a man named no Austin Powers. So what is it now? You can say
Base to the power
b
equals answer.
to the p equals a. I love it. Oh, it's a equals b to the p. I'm sorry. You're right. All right. Now here's where things get a little bit harder. Do this the other way. What I mean by that is rewrite in logarithmic form. Seven to the m equals 1. Don't say it out loud. So this is a little bit less easy. You know what the base is for sure. What's going to go under the log here, like right there? Because the base is 7. Now the answer to a log is always a power. So what's the power?
M.
So where's the only place left for y? There you go.
Easy.
And remember, the output of this guy must be the input of this guy. So that way is not as easy as the other way, but it's still something you can attack. You can put it together. Hopefully. And then how do you check yourself? 7 to the m equals y, sweet. You with me? A little bit? So logarithms are not difficult. Not. Properties of logarithms are a little bit harder.
Is that 4.4?
Oh yeah. So real quick, before we get out of here, get out of this section.
I think you do that.
There are certain phrases that if I'm not careful, the minute I say it, all the backpacks suddenly are coming out. You know? Like if I say next time we'll be no, we're not leaving, I'm just telling you what we're gonna do next time. Alright. So look at this homework. This is page 322. Oh. So, I mean, the first few are pretty simple. The concepts, not too bad. The skills, they want you to rewrite logarithmic to exponential like we've just been doing, right? So that's basically 5 through 12, actually 5 through 18 are rewrite from exponential to logarithmic or the other way around. You guys decently with me? And they make it a little bit more interesting when they do something like this. Just a little bit more interesting, not that much more interesting. How would you rewrite this in logarithmic form? Base A of m equals what? Right, the power's always got to be here, the base has always got to be down there. There's only one place left for the last 2 is in there. It's not really an easy to remember phrase, sorry. Then they ask about evaluate the expression like we were doing just a second ago. One of the funniest ones to me is something like this. Let me see if you guys see why this is easy. What's log base 11.7 of 11.7 squared? Yeah, 2. What do you raise 11.7 to make it 11.7 squared? To the second power. Isn't that silly? And just to make this even more of a point, what's the cube root of y cubed?
1.
Why?
Is it a
Because the
1?
cube root and the cube
Cancel.
cancel. So what happens with log base 11.7 and 11.7 to a power? They cancel. Because aren't these inverse functions? Isn't that where the hell this stupid thing came from? We graphed its inverse, and we just had to come up with an expression, a little symbol, and came up with a log. You guys kind of with me? A little bit. So what about this one on the heels of that one then? What is 7 to the log base 7 of 8?
That's it.
That would have been funny. Go ahead. Sorry. If I put a 5 there, and it's basically 1, 2, 3, 4, 5. That would have been a little freaky. Because what's happening with 7 to a power and log base 7? What do they do to each other?
They cancel.
So what do you
So
get?
it's log 8.
Careful.
Or
The log base 7 and the 7 cancel, so the answer is 8. Let me analyze this a little bit more. In fact, this is kind of cool. What does this represent? What does it always equal? If I put a number there, what would that number do? What does log base 7 of 8 represent? The what that does what?
The power that makes
Power. See, now some of you guys just think I'm crazy. The power, right? Log is always equal to a power. The power that does what?
makes 7, 8.
Makes 7 become 8. So if I raise 7 to that thing, it will become 8. So if I raise 7 to that thing, it will become 8. Log base 7 of 8 is the power that I raise 7 to make 8. So when I raise 7 to it, I make 8. Now, personally, I don't like that way. It's much easier. Bam, it's freaking 8. Right? They're inverse functions. They have to cancel. We know that.
What if they're different?
Then you can't do that. It's just like, what's the 4th root of x cubed? Can you do shit with that?
no.
No. So what's 6 to the log base 2 of 9?
Something.
Something. I don't know.
Oh, so that would be the answer?
Now, you can't really simplify that directly. Could play with it a little bit. Sort of like if I was 4th root of x to the 5th, couldn't I do a little something?
But we don't want
Because there's 4 goes into 5, you could kind of simplify it. So you can do similar things with logarithms, but not there yet. Okay. Let's see. Oh, there we go. Solve.
Oh, that's easy.
Yep. Because what's x? X 3 to the 4th is x, so x is 81. Sweet. So you have that whole little section. Everything I'm doing on the board, by the way, is just what you're going to see in your homework directly. So I can talk all about the concept, but I got to remember to go back and show you nuts and bolts. What are they going to be asking you? What am I going to be asking you too? Oh, and blah, blah, blah. There's a sketching of graphs. Ah, here we go. Here. So keeping in mind that the graph of any log that has not been to any base you want is going to be roughly this. Cool. Which means what about the domain? What x's can you definitely not use?
Negative. Or zero.
And 0. I love it. So the domain must be from 0 to infinity, not including 0. So far, so good. See, that's close to like the square root of x. What's this guy's domain? Yeah, it can equal 0 to infinity. You with me? Logarithms can't equal 0. Can't raise something to a power and make it 0. So, what's the domain of so what does it say? The inside of the log has to be greater than 0. You remember when we start talking about domains? If you can say it in English, you can write it in Mathish and solve it. So say it. The inside has to be greater than 0. Now how do you write that in Mathish? What is the inside? 2 minus 7x. 2 minus 7x. The inside must be greater than 0. Solve it. You're done. So I don't care how funky the function gets. You just have to have some basic knowledge of what it looks like and be able to say it in English. Just what can't happen or what must happen. You with me? Like a rational expression on the bottom cannot be 0. So that's exactly what we write and we solve it. Here the inside of a log must be greater than 0. We solve this. X is less than 2/7. Yes, ma'am. What about the negative? Sorry.
A negative.
Oh, yeah, sorry. I just add the 7x, divide by 7. Yeah, cool. Either way you do it, it's got to change that sign somehow. Either the x moves to the other side or the sign changes. Cool. Yes?
So back to your, way back when you had, what was it, 3 to the x power equal 11, how would you solve that?
Almost there. The problem with that is I could rewrite. I know the first step to do this, I just don't know how to do it from there because I don't have a log, the appropriate log button on my calculator, right? So how can I do, what's x equal then? How can I rewrite this in logarithmic form? Log base what?
3 of 11.
There you go. So I know at least x, there you go, I solved it. That's the exact answer. Sort of like giving me square root of 7 instead of a decimal approximation. But I still need to kind of know how to figure this out. You know, I'm not going to say to somebody, how many chairs do we need? Log base 3 of 11, approximately. Who the hell are you? So I still need to figure out how to do that. And to get there, I got to do a couple other things. First thing I've got to do is, what's one base that's special?
10.
Okay, I like it. There's 2 bases then that are special. There's base 10. Why is 10 special? It's special just like a square root is special.
That's what you're calculating.
Because what's the understood root? When I write this, what's understood to be there? You would never see this, right? Not much. You just did, I know. But you wouldn't see it as much. It's an understood 2 there. So base 10 is called the common logarithm. And it's the one that we use, well, and why do you think base 10 would necessarily be
It makes whole numbers.
common special base? Because our number system is based on 10. There you go. And who knows, especially living here in California, what they use common logarithms for to describe things that sometimes happen in earthquakes, yeah. Right? The Richter scale is based on log base 10 of a ratio of things. So that's why a scale 5 earthquake versus a scale 5.7. 5.7 is a lot more destructive than a 5 is, because the scale now is logarithmic. Every change of 1 is actually a multiple of 10. You kind of with me? So a 5 on the Richter scale versus a 6 is 10 times as powerful. The 6 is. You semi with me? Okay. So base 10 logarithm, we just write log x. That's understood to be base 10. So what's log of 10,000?
100. Yeah.
10.
No, 1,000.
I think I've heard it yet.
1,000.
4. If anybody said 4 before, I'm sorry. 10 to the first is 10. 10 squared is 100. 2 zeros. How many zeros do you see? 4. So 10 to the fourth is 10,000. Be really careful. This is not multiplication. This is, well, exponentiation I know is multiplication, but this is exponents. What do I raise the base to make this? I need 4 tens multiplied to make 10,000. How would you do
You do it slowly.
Second?
Steps.
Yeah. A way to rewrite this question, if you put an X there because you don't know, how can I rewrite this? What's the base?
10.
10 to the X equals 10,000. These ask the same thing. That's what we were saying earlier, right? These ask the exact same question. What do I raise 10 to? What do I raise 10 to get 10,000? If you know your scientific notation, every 0 is another 10 that you need. So that's first, second, third, fourth power. So that's why X is 4. Okay. Another thing that you use logarithms for is decibels. You ever seen a chart that says a rock concert is 120 decibels versus a jackhammer is 110 or whatever? You with me? I'm trying to tell you how much your ears are going to hate you later in life. Or later that night. Okay, so we're closer to doing what we need to do. What's the other special base, do you think? The only other special base we talked about earlier? E. This is the only time you'll see me write log base E of X, because what you really write, ln, natural log. So that explains why your E button is right above the ln button. Where's your 10 to a power of X button? Right above the log button. You with me? It's incredible how they did that for us. The inverse function is next to the button for the original function. Okay, cool. You guys, so far so good?
Yeah.
Okay. So, let me think. I'm almost to the point where I can do this. Need a little bit more. Because the question somebody had was, how do we solve this? And we got this far, right? We're still not sure how to do that. I think if it can get us there. Yes, yeah, I can. Sort of. No, not quite. Sure. All right. So I've got to do some properties of logarithms. And this will be the last thing we talk about. We'll talk about the properties of logs. I'll show you how they would actually help us solve this. We're not going to get to the section where we actually solve logarithmic and exponential equations.
That's 4.4. Properties of logs.
It says log.
We're going to get to 4.4. We're not going to get to 4.5.
So that's what the test can go up to, 4.4?
Test will go up to 4.4. Yeah.
Properties of logs is 4,4.
So
Properties of logs is 4.4. Yeah.
for homework, we just stop at 4.4.
Stop at 4.4 for your homework. Yes.
So 4.4?
We will. We haven't talked about 4.4 yet. You should have said we should need to stop at 4.3. I'm going to go based on what you said. All right. Now, I told you earlier, you should not have any problem with the basic logarithmic equation. And that's where students have a lot of trouble for some reason. We don't have any trouble with that now, do we? Log base 4 of 16, what would that be? Log base 4 of 16?
2.
2, because I squared 4 to make 16. Nothing more than that for that, right? Where I understand if you have a little trouble is with properties of logarithms. What's going to get you through this is remembering what a logarithm is. A logarithm is always equal to a power. So logs are powers. So shouldn't their properties be the same as the properties of powers? And properties of powers are damn easy. When you multiply, you add. When you divide, you subtract. Blah, blah, blah. Right? Semi-decent? Okay. So for example, let me go the same order that, it's a good order to go. I'll use the same symbols they do too. So these logs are any base really. I think they, yeah, there you go. They put a little a there for it. Base. So we're gonna semi-prove these. The proof gets a little disgusting if you want to do a true proof. Basically, I'm gonna take the log of the product. So what's the power after you take the product of two things? What do you do with the powers? When you multiply things, what do you do with the powers? You add them. So, you know, like if A was 10 squared and B was 10 cubed, A times B will be what?
10 to the 5th.
10 to the 5th. So that would mean that the log of AB would equal the log of A plus the log of B. You with me? Because what's the log A? Right, let me slow down a little bit. I guess I am going to try to semi-prove this. What's log A? If A is 10 squared, what's log A?
2.
2, sweet. Let me make sure we're all together. Since I wrote log, what's the base?
10.
10, because I'm using base 10 up here, right? So log A would be 2. What's log B?
3.
3. And what's log AB? 5. So isn't log AB equal to log A plus log B? And again, the properties are easy. Because I am going to assume everybody in here knows your properties of exponents. I know this is true. So the property of log is the same damn thing. When you multiply things, you add their exponents. Now, of course, when you multiply two things with the same base, and I know they have the same base, because they both have an A, they have the same base. So I can add the powers. Don't make it any more than that. Be really careful. Can I do a damn thing with this? You know the answer by the way I said it, but still. So let me say it different. Why can't I do a damn thing with that? Because powers don't work well with pluses, do I? I can't distribute powers to a plus or whatever, right? I mean, what's 10 squared plus 10 cubed? Can it do anything with that? Not directly. I could rewrite them, but still.
Can we just so log A with A?
No. That's lowercase a, so it's different. With me? Yeah. I should use a little. I'm using the same symbols they have in the book. I understand where you're coming from, but to tell you honestly, to increase our variables, lowercase and uppercase are different. So I could use a little n there. It might have been better. Is everybody cool with that? So big A could be 10 and little a could be 3. They don't have to be the same thing.
So division will be subtraction, right?
Incredible. So if I have log A, I'm not. I'm just. Like the nicest teacher there ever was. That's amazing. So what do you do here? It's the same. It's like you just said. How would I rewrite this?
Minus.
Be more specific.
Log
Okay.
A.
Log base A of A minus
Minus.
log base A of B.
Base of A.
I like it. Okay. Real quick little side note while we're doing this, just to give you something more practical here. If I had log 7, let's see, of 56 minus log 7 of 8. Could you do either one of these by themselves?
Yeah.
Are you sure?
No.
Because, I mean, 7 squared is 49, 7 cubed, that's too big, right? And 7 and 8, they don't go. I can approximate it. This is roughly a little more than 2, and that's roughly a little more than 1, so it's going to come out roughly around 1. That's not good enough. So how can I use a property to help me? They work both ways, of course, like math always does.
56 minus 8.
Don't judge it. So if I have this, I should be able to rewrite it as this.
Mm-hmm.
So that would be log base 7, because the bases are the same, right? Log base 7 of 56 over 8. And 56 over 8 is
7.
7. So I took two parts. I couldn't do either one of them, but the property helped me put them together and make it something I could do. That's nice.
Mm-hmm.
All right, and the last couple properties, there's only one more really, but oh, so real quick, coming off of look back at 1. What do you think log of a times a times a is? Using property number 1. So it would be log a plus log a plus log a. You with me? I mean, that's just using property 1 over and over and over. Are you okay?
Yeah.
Nothing major. Log of a times b is log a plus log b. So log of a times a is log a plus log a plus log a. I'm just using a property a few more times. Nothing major, is that cool? Nothing major. And that's like somebody said, 3 log a. And of course log a is better known as log of a cubed. So there's a generalization I can make here. Any power on this can effectively come down. And think about it. What do I do when I raise something with a power to a power? What do I do with the powers? Like x squared cubed.
Multiply them.
You multiply them like I'm doing right there. It's still a freaking property of powers. It's silly. So if you know your property of powers, you know your property of logarithms. They're the same. This is the one that's going to save our ass on solving equations. So that's basic properties. Now, I told you I'd go through the properties, and I wanted to go back and show you this, and then we'll call it a day. So we'll still get out here a little early, right? I haven't let you out early for a while, so what the hell? So picking up where we left off here, I can't do shit with this. So let's do something a little different. Let's not go that way. Can I do something? Now, the main problem with my variable, for example, if I had this, I'm going to want to do what for the first step? Yeah, because the x is stuck on the bottom. I'm going to multiply to free it up. Where's my x stuck now? In the variable. If I only knew a function that would bring a power down, and of course we do, we just found out that logarithms will take a power down, right? So I don't have to use log base 3. Why don't I want to use log base 3? It's not my freaking calculator, right? So I want to use log, for example, or ln. Tell you honestly, I normally use ln because there's one less letter to write. That's true. You'll see that's true for most math people, by the way. So I'll just go ahead and do it. So now I really want you to understand. The same way if I had x cubed equals 7, how would you solve this? You would take the cube root of both sides.
Yeah.
So if I have 3 to the x equals 11, how do you solve it? I would take the ln of both sides. You cannot divide by ln. I am not multiplying both sides by ln, dear God. You with me? Just like I'm not multiplying both sides by the cube root symbol. I can't divide the cube root symbol away. Yay! So be careful about that. This is a function of something. But what can I do with this now? The power can come down. I've freed up my variable. Logarithms are inverse functions to exponentials. I should use a logarithm to solve an exponential equation. So that takes my power down, just like we saw in that last property. And now I'm maybe 2 steps away. 1 step away from getting the exact answer. What do I do at the end? Divide by ln 3. So there's the exact answer. Can somebody help me out? Just do ln 11. Be really careful, because when you hit your ln, I think it opens a parenthesis. If you have an older model. Maybe have a newer model that where your square root grows. You know what I'm talking about? Do you guys understand what I'm saying?
Yeah.
When you hit a square root button, does anybody have something that doesn't open a parenthesis? Hit your square root button for me right now. Help me out. Humor me. I'm a teacher. Make me happy. Hit the square root. Does it not open a parenthesis? That's what I'm talking about. Then you would be. I want to see what it does next. Oh, so over there. Well, for ln, it also opens a parenthesis. Too bad for you. So the point here is when you put this in the calculator, you're going to do this. Be sure you close that damn thing, right? If you just say divided by, it's going to put ln of 3 inside there. It's freaky. ln 11 close, divided by ln 3. 2.18, blah, 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 blah. So what does that mean? What does 2.18 do?
That's the power
Associated to our problem. If I raise 3 to 2.18, you can try it. It's not going to be exactly 11 because this is not the whole number, is it? But do 3 to the 2.18 power. That should come out to be, I don't know.
2.
Sweet. Pretty damn close to 11. How we doing?
Good.
Wait, what did you in the last part?
Just divide those two there. Oh, the last thing I did was if you do 3 to the 2.18, yeah, we're just checking it like way back in algebra.
3 to answer your
All right. Oh. I didn't necessarily not give this to you until now and keep you here, but it worked.
awesome. What is this?
Take home project. That was correct.
Awesome.
So just like last time, I'll have the answer key for this next time.
Hey, what's what does it cost? Like $60 or whatever?
Yeah, it's like 55 or something like that. And then you
Course number?
yeah, you have course number and then you have to type in the college GCCD and then
It might be the same as the 89. Is there a mode button? That's up to
Google.
How do you get away from scratch? Actually, the